My esteemed listeners, in this tutorial we discuss about, or we bring to the fore, another interesting algorithm design strategy coming to be called as decrease and conquer strategy. Okay, in the previous 3 volumes of our tutorial we discussed divide and conquer strategy, and there is it is going to be increasingly understandable that there is a substantial difference between decrease and conquer strategy and divide and conquer strategy. Decrease and conquer strategy basically exploits or tries to establish the relationship between solution to a given problem and solution to the smaller instance of the same problem. That means to say, in every iteration of the algorithm there remains one portion of the unsolved problem and the solved portion of the problem, the solution to the same problem. In the beginning iterations of the algorithm, the unsolved problem instance size will be much bigger than the solved portion of the instance size. And as a difference to divide and conquer strategy, okay, this decrease and conquer strategy comes with 3 versions. Okay, and you must remember that there existed only one version as far as divide and conquer strategy, that is, divide the problem till the problem will not be further divisible, then find the solutions for the small instances of the problem, then integrate the solutions into a total solution for the given problem. That was the strategy. But here decrease and conquer technique or decrease and conquer algorithm design strategy comes in 3 versions. One is decrease by a constant size. Decrease the size of the instance by a constant size. This constant size happens to be normally 1. Decrease by a constant factor. So the instance size is iteration by iteration will be reduced by a constant factor, and this constant factor happens to be half. And there is another version of the algorithm design, that is, it will reduce the instance size iteration by iteration to a variable size. It's a variable size decrease. It will be usually a huge reduction in the input which cannot be predicated or which cannot be predicted beforehand. And we will take examples to understand as to how decrease by a constant works, and as to how decrease by a constant factor will look like, and as to how the variable size decrease will happen. Decrease by a constant. Let us say we need to find a to the power of n. We need to find a to the power of n. Okay. This a to the power of n can always be written as a to the power of n minus 1 into n. Here the relationship is multiplication, and this is the solved portion of the problem into a. This is the solved portion of the problem, this is unsolved portion of the problem. And its successive iterations, this becomes a to the power of n minus 2, and this becomes a square. It is something like this. Okay, a square is the solved portion of the problem, and a to the power of n minus 2 is unsolved portion of the problem. Okay, this is by, so every time it is a reduction of only 1. And if you want to add a1 plus a2 plus a3, okay, etc., up to a to the power of, a n minus 1 or a n, what we have to do is, okay, a1, okay, plus a2 plus a to the power of a n minus 1 plus a n. Next, a n minus 1 plus a n. So this is the solved portion of the problem, this is unsolved portion of the problem. In the beginning cycles, in the beginning iterations of the algorithm, the unsolved portion of the problem is much bigger than the solved portion of the problem. Okay, here there is a reduction. Once we take out one of the elements or one of the components of the solution, we no longer revisit this, and the size of the problem is reduced by 1. That is the meaning. Decrease by a constant factor. Okay, on the other token, in the same token, a to the power of n can also be calculated as, computed as a to the power of n by 2 whole square. N by 2 whole square. If n is even. If n is even. This is a caveat. This is a condition. Otherwise, it can be solved something like this: a to the power of n minus 1 by 2 whole square into a. If n is odd, but n is greater than 1. Here also n is greater than 1. It will be equal to a if n equal to 1. In all the cases, we should observe, okay, a portion of the solved problem and portion of the unsolved problem. Okay, this is the thing. So here the factor is by 2, 1 by 2. It is something like that. And the variable size decrease, the best example that we can quote is finding GCD. Okay, we know, okay, in our previous discussions, in the initial discussions of this design and analysis of algorithm, we chose to give the best possible algorithm to be which is non-ambiguous, which has well-defined steps, which has defined inputs, and which will stop ultimately, is the Euclid's algorithm for finding GCD. What it says, GCD of m comma n can be written as GCD of n comma m mod n. Okay, this is how we wrote, and this is the algorithm. Of course, this is the algorithm proposed by Euclid. We'll take an example. We will see how exactly the instance size will go down variable to a variable account. Okay, we will take an example of, say, 60, 25. 60, 25. Okay, two numbers, they are integers. Anyway, it can be written as GCD n. Okay, n will come over here, 25 will come over here, and here the second number will become m mod n. M mod n means 60 divided by 25 and whatever the remainder that comes back. Okay, it is 25 2s are 50 and what remains is 10. Okay, 10 will remain. Now you can see over here 60 became 10. 60 became 10. Okay, 60 which was here became 10. So that is a drastic reduction that you can notice. And once again, this can be written as GCD. Okay, n will occupy this place, 10 will occupy this place, and it is 25 mod 10. 25 mod 10 is 5. Okay, now 25 became 5. That is the thing that you should notice. And GCD, once again, GCD 5 will be over here, and 10 mod 5 is 0. Therefore, the algorithm returns m as the answer. M is this. Okay, therefore GCD equal to 5. So in every step, so the problem will be completed much earlier than the other two versions. But this particular version is not applicable for all kind of problems. Okay, wherever number theoretic algorithms or number theoretic problems can be tackled by decrease and conquer technique under variable size decrease strategy or version. Now, the first example, a legitimate example, a famous example is insertion sort. It is believed that insertion sort vaguely mimics the play of cards. Okay, when we play the cards, we will arrange the cards in a particular fashion. Okay, some of us may try to arrange the cards taking this as the anchor or taking this as the anchor. Okay, or this must be the starting point. We will keep it aside. Okay, we don't disturb this. We will pluck this card. Okay, we will take out this card and we will compare with this card, and if it is to be placed in front of this, we will leave it here only. Otherwise, we will take it and put it over. We will insert behind this 5. Similarly, and those two are arranged now. Then 8 will be plucked. This card will be plucked up and it will be compared with this card. Okay, if this is not in the order, this will be placed behind this, otherwise it will be left here only. Okay, it will be placed behind this. Once again this card will be compared with this card. Okay, as far as this number is concerned, if it is more than or less than whatever the order that is to be maintained, it will be placed either the behind of this card or in front of this card. This is how insertion sort. It vaguely mimics the play of cards. The nth element, every time the nth element is assumed to be sorted, and this is assumed to be sorted, and the n-1th element, okay, here is 0, here is n-1th element. N-1th element is lifted and arranged with respect to the nth element. This is how it happens. Okay, this is how it happens. Right. We will just go further. Okay, we will remove this anyway. Right. Now, we'll go to the next slide. We'll take an example. Okay, you have to carefully follow this anyway. Right, 99, 55, 78, 100, 39, 44 and 27. Okay, 99 is assumed to be sorted. This is the last nth element. Okay, 55 is to be inserted either behind 99 or in front of 99. Okay, since we are arranging things in ascending order, presumably, okay, this 55 has to go behind this 99. Okay, and here literally the swapping doesn't take place. Okay, the sorting will take place by virtue of movement of the elements, some kind of a lateral movement of the element. In doing so, overwriting happens. Okay, so there are chances. Okay, why chances? We will miss this 55 if we just shift this 99 over here. It will be 55 will be overwritten. Therefore, in order to avoid this, 55 will be stored in a container. Okay, temporarily. Now there is an index which will move from here in this direction. Okay, which has the extreme boundary to be equal to n-1, and there is one more index over here which will move in this direction and which can move only up to 0. Okay, only up to 0. Okay, so therefore all the time j should be greater than or equal to 0, but I should be lesser than or equal to n-1, lesser than or equal to n-1. So in the first cycle, okay, j position will always be 1 less 5. Okay, j will always be equal to, in the starting of the iteration, j will always be equal to i-1. Okay, that is another important point, and it is only the ith element which will be stored temporarily because of in order to avoid the loss of element. So this 55, see this the thing in the container is compared with this element. Since this is greater than this, okay, this will be moved to, so j plus 1th position will carry whatever that was in j. So the element in j will be moved to the position of j plus 1. Then j will come back. Okay, then j will come back. So j will occupy -1. Therefore this C55. So a of j plus 1 will be equal to c. Okay, so this position will be filled only upon j going in this direction. Okay, it will be fitted over here. Then 55 comes over here, 99 comes over here. Okay, so this is the small portion of the array which is already sorted, and this is the portion of the array which is not sorted. This is being related by plucking an element, placing it in a container, and making this particular other elements to move laterally by overwriting. Okay, now 78, see whatever that is in C, this is the ith position and this is the jth position. So j can move now. Okay, in the second iteration j can move at least to 2 positions, I can move up to n-1. Okay, now 78 is compared with this 99. Since 99 is greater than 78, 99 will be moved to aj plus 1. So aj plus 1 will carry whatever that was there in j, and j will come over here. J will come over here. This 55 is compared with this. Anyway, 55 is lesser than this, therefore this particular so A of j plus 1, this is j has gone over here, so A of j plus 1 will carry whatever that is in C. So 78 will come over here, 55 is there, 99. Okay, this portion of the array is started. Then it is a chance for 100. So 100 will be plucked and it is kept in a container. Once again, 99 is compared with the 100. Okay, I is here and j is there. I is here and j is there. Okay, so A of j is compared with this C. Therefore, since this is greater than 100, so 100 is greater than this 99, it will be kept there only without any shift. Okay, next once again. 39 is a chance for the 39, this element. So 39 is stored in a container. So here is I, here is j and here is I. Okay, so A of j is greater than whatever that C contains. Therefore you should move over here. So aj plus 1 equal to A of j. Okay, then j will come over here. So this is compared with this. Once again it has to move because this is greater than that. So A of j plus 1 will be occupied by 99, j will move back. So this will be compared, A of j is compared with this. A of j is once again greater than whatever C contains. Therefore A of j plus 1 will receive whatever that was there in A of j. J will come over here. Okay, A of j is compared with this and see this is bigger than that, therefore it will be shifted to j of plus 1. Aj plus 1 will receive whatever that is contained in A of j. Okay, and j will come back over here. Then A of j, okay, then the 55 is compared with the 39. Okay, 39, therefore 55 will be moved over here and 39 will occupy this particular place. So this particular place is once again designated as j plus 1. Right, now 44, it is a turn for 44. It is stored in this container. It will come back, this is compared and this is moved to this position. Okay, this is compared and this is moved to this position. 78 will be moved to this position. 55 will be moved to this position. 39 will never be moved and 55 will go over here and this place will be occupied by whatever C contains. By the time j will have gone over there. Therefore aj plus 1 equal to whatever that C contains. Right, next is the chance for 27. So 27 has to move. Okay, as I told, as the algorithm progresses, the solved problem size increases and unsolved problem size decreases. Anyway, the relationship is compare and insert. So 100 is greater than this, therefore 100 will move to this position. J will come over here. A of j is compared with this, it will move over here. Then j will come over here. Like this, j will keep on moving. J will come to this particular position. Okay, then this is compared with this. Okay, this is compared with this. Anyway, this is greater than that. Therefore A of j plus 1 will be 39 will go over here. Okay, 39 will go over here. J will become minus. J will occupy this particular position. Therefore it will be this will be definitely overwritten by aj plus 1 will be overwritten by whatever that C contains. This is the algorithm. So we have seen shifting, and every time one of the elements which is plucked from the unsorted array group and it is inserted in the appropriate position. Okay, it is inserted in the appropriate position. Okay, right. We will write the algorithm insertion sort. Okay, this is the title of the algorithm, name of the algorithm. What it does, it sorts the given array by insertion sort. Input an array A0 to n minus 1 of n unordered elements. Output array A0 to n minus 1 sorted in ascending order. Okay, now we will definitely write the algorithm for ourselves. Okay, now it is a chance for I, for I which moves from 1, because the nth element is assumed to be sorted, therefore it has to start from that point. Okay, it will never start from 0, it has to start from 1. Okay, we have shown that in the previous slides. 0 to n minus 1 do. So this is the boundary for the movement of I. It will start moving from 1, it will go to n minus 1, and we had a container C, and every time, okay, C contains A of I. Okay, it is A of I which is to be plucked, which is to be lifted, and which is to be inserted. A of I, and J will go to a position I minus 1. Okay, in every beginning of the algorithm cycle or algorithm iteration. Okay, now we will try to put up the condition while okay, J is greater than or equal to 0 and A of J, the previous element, okay, previous element when compared with the lifted element. Okay, the lifted element was in I, which is nothing but J plus 1. Okay, the previous element is in J. So A of J, if A of J is greater than whatever that C container contains, do. Okay, if this is true and this is also true, okay, J has not reached its extremity and A of J is greater than C, then what you have to do is A of J plus 1, then you have to literally shift. A of J plus 1 is equal to A of J. A of J. The previous element is to be shifted to the next position. Okay, simultaneously after this J should be reduced by 1. So it has to start moving in the backward direction. J equal to J minus 1. Okay, so this while loop will break either this thing becoming false or this thing becoming false. Okay, in the first cycle we have seen J going to negative position, therefore loop will lose the control, it will come out, then we will fill up A of 0, that is J plus 1 in the first cycle, to be filled with whatever C contains. So this is the algorithm, my dear friends, this is the algorithm. Okay, I moves from 1 to n minus 1. In every iteration, starting of the iteration, A of I is preserved. The element that is plucked from the unsorted array is preserved, because it will go erased, it will go overwritten otherwise. J will be having a position of I minus 1 and J will start moving in backward direction as the iteration goes on, and I will go on moving in the forward direction. Okay, one movement of I will cause several movements of J. This is the understanding about this algorithm. Now we will write the complexity. So J moves from 0 to I minus 1 or I minus 1 to 0. When we put the limits, it should be 0 to I minus 1, while I moves from 1 to n minus 1, and this is the comparison. And this is the comparison. There is only one comparison that is available in the while loop. So therefore we will go to the next thing and we will analyze number of comparisons in the worst case of insertion sort. In the worst case of the insertion sort, okay, as a function of input size n equal to, okay, the inner while loop where there is only one comparison, and the limits, okay, J moves from 0 to I minus 1. Actually, as far as movement is concerned, it is from I minus 1 to 0. Since we are putting them as limits, it is 0 to I minus 1. And this is repeated as I moves 1 by 1. So as I moves from 1 to n minus 1. Okay, So what we get here is you have to expand this I equal to 1 to n minus 1, this becomes I minus 1 minus 0 plus 1, so I. So this is expansion of arithmetic series where n happens to be n minus 1, therefore it is n minus 1 into n plus 1, so n minus 1 plus 1. In place of n we are writing n minus 1, therefore it becomes n divided by 2. So it is obvious that the worst case of insertion sort belongs to big theta of n square. It is of quadratic complexity. It's of quadratic complexity. Right. Now there are some problems left over here. Okay, I will give the hints anyway. Apply insertion sort to sort the list example in alphabetical order. Okay, that can be done anyway. So we will have a sheet over here, we will have a slide over here. Okay, yeah, for solving these problems, right, for solving these problems. So this is apply insertion sort to example. I will show a bit of it and I will leave it to my respected listeners. Okay, example, E is assumed to be sorted, EX, A, MPLE. This is to be lifted. Anyway, this is alphabetically superior when compared to this. They remain as it is without any movement. Okay, A, MPLE, like this. Okay, I will show only for 1 or 2. Okay, the rest of the things we will be able to do that. So A is plucked. Compared with this, it should come over here. Okay, once again E is compared with A, so A should come over here. So A will be kept in a container. Okay, as you know. Okay, you can trace in a similar way. So A is placed over here. So the contents of this container is compared with X. This is greater, therefore it will be shifted. So A will come over here, E is here, X is over there, then M will be taken up. It is like this. It continues in this fashion, right? It is continued in this fashion. Next one. A regiment of n soldiers must cross a wide and deep river with no bridge. They come to know that 2 boys of 12 years each are playing with a teeny boat. This boat can carry 2 boys or 1 soldier at a time. How can soldiers cross the river and leave the boys to the boat? How many crossings are needed? So they can do like this possibly. Okay, this is the river and here is the boat. Okay, now first of all they will allow both the boys to go over here. Okay, one of them will get down. Okay, one of will get down, the other will bring. So one movement has already happened. The movement here is movement of the boat. Anyway, this will come again with one boy navigating that boat. So this is the second movement, and once again a soldier will move with the boat. This is the third movement, and he will drop over here. Soldier will come over here, and once again he will send the boy to this. So 4 movements will take. In order to move 1 soldier, there are 4 movements of the boat is required. There are n soldiers, therefore it requires 4n movements. So every time one of the soldiers, only 1 soldier will cross the river, therefore it is reduction by 1. It is reduction by 1, decrease in reduction by 1. Okay, consider the following version of the insertion sort algorithm. It is written something like this only in the previous thing only, but here there is no container. J will become I minus 1, justifiably so, and J is greater than or equal to 0, and the condition remains same. A of J is compared with A of J plus 1. A of J plus 1 is the element which you have plucked or which you are trying to pluck. Okay, then swapping takes place. This is a legitimate method. It simply works. There is no difference between the algorithm that we discussed and the algorithm that is given over here, except for the fact this will also suffer from quadratic complexity because it runs from 1 to n and this runs from 0 to I minus 1, therefore it becomes n square complexity. But there the there is no swapping as such, because swapping involves 3 steps. Okay, A of j is to be poured in a temporary container and this should get vacated, and to this A of j plus 1 is to be filled, A of j plus 1 is to be filled, and A of j plus 1 is to be vacated, and whatever temp contains is to be poured into this. So there will be 3 processes in swapping. Okay, that is avoided in the earlier part of the algorithm. That is the only difference. Okay, what is the efficiency? Efficiency remains the same. How it compares with the algorithm with the explained in this tutorial? So this has a drudgery of swapping. Okay, many swappings. Okay, now the other problem, let us see. Okay, there are 2 n glasses standing next to each other. Let us say if n is 4, 1, 2, 3, 4. Okay, the other 4. We will select a different color, the other 4. So 2 n glasses. Okay, 2 n glasses. There are 2 n glasses standing next to each other in a row. The first n of them is filled with soda. First 4 of them is filled with soda. Okay, and the other remaining n glasses are empty. These are all empty bottles. Okay, these are all empty bottles. Make the glasses alternate in a filled empty pattern in the minimum number of movements of the glass. So here movement means lifting one of the glasses and pouring the contents to the empty glass. Okay, that is the thing. Okay, right. Therefore we will select this glass, okay, which is full of soda, and we will fill it up over here. One moment. Okay, then this is left as it is. Okay, and this is selected and it will be filled with this. Okay, so how many swapping? So this is filled with this. Okay, so this is fully filled. This will become empty. This will become empty. This is filled, and this is filled with the other one. So now there are 8 bottles n, and number of movements is just 2. Therefore if there are n bottles, filled bottles, it will be n by 4. N by 4 movements will take place. Okay, this is the thing. Okay, this you try to understand and you take a bigger value and just try. Okay, this is empty, this is filled, and this is empty. This is filled and this will become empty. Okay, and here again this is empty, this is filled, this is empty, this is filled. Right, with this we will complete this. Okay, anyway, until then, bye, and we will come back.